to this. At the bottom of the website, there's the table with all the chapters. So for each chapter, there's the slides. Again, there's the old PDF worksheets that are not perfectly aligned with what we're doing now, but at least that if you want to print them out, it has places to show your work for, or if you want to work ahead before I get them on Canvas. And then there's the RMD. Now these RMD skeletons, I would not download them here. There's something going on wrong about downloading from GitHub. So, but I'm going to go here to get the slides. So I'm going to start with Chapter 1, Variable Scales, Rounding, and Summation, and it's an HTML. If you click there, it should open up the slideshow. And these slides that are HTML were written in R. So that's kind of handy for me, and it helps show you some of what R can do. So this is a nice diagram. I know on the discussion board there was the point, you know, remembering the names and how you determine what type of scale there is. And the type of scale of variable or measurement is not always as clean cut as we would hope it would be. So there is this continuum of complexity of measurements. On one end, there is completely categorical, discrete, no order. Nominal variables, and I remember them because nominal name is the name of categories. So it, like colors, red, blue, green, orange, county someone lives in. They're completely separate and distinct, just the name. Genders, there's no inherent order. We can always give numbers to them, but they don't have an inherent order that someone would automatically say, oh, the order should be this for the nominal. The second type of categorical variables are ordinal, and the ordinal have order to them. So there's some kind of rank. And when we do counts or places, 1, 2, 3, 4, there is order, even though they are discrete, that you can't really be between. So you're in first grade or second grade. No one's really in grade 1.5. Usually that doesn't have any meaning, or grade 1.83. Interval is where we do have numbers and order, but each 1, 2, the difference between 1 and 2 is the same as the difference between 2 and 3 is the same as the difference between 9 and 10. And then ratio has the additional complexity that 0 means none. And there are things that kind of fall somewhere in the spectrum. The most problematic or kind of fuzzy one is Likert items. So Likert items are usually, we have some, like the really common one is how much you agree with something, and they're like strongly disagree, somewhat disagree, neutral, somewhat agree, and highly agree. It's a continuum, but we're kind of putting labels along the continuum. And a lot of times these will be numbered, like 1 is strongly disagree, 2 would be somewhat disagree, 3 would be neutral, and so forth. So on this continuum, there is definitely order, but is that order interval? Is the difference between strongly disagree and somewhat disagree, is that difference, that interval, the same size as between neutral and slightly agree? Can you argue that those gaps between levels, or all the gaps are exactly the same difference, the same size? And that's the catch with Likert items. Likert items definitely would be ordinal, but are not guaranteed to also be interval. That those gaps are not always, we can't prove that they're equal. Temperature scales like Fahrenheit and Celsius are interval, because the difference between 5 degrees and 6 degrees is the same as the difference between 90 and 91 degrees. A 1 degree difference means the same thing no matter where we are on the spectrum of degrees Fahrenheit. So degrees Fahrenheit or degrees Celsius is interval. Likert items are, for all intents and purposes, should be ordinal, but they get treated as if they were interval. And should we or should we not is a conversation that keeps on going, because it depends. This is like my most common answer I give to people that come for consultation. They're like, can I do this or should I do this? And the answer is almost, well, it depends. And it depends on a lot of things. So with Likert items, Some general rules of thumb that are often put into play are things like you can treat an ordinal Likert item as if it were truly interval, as long as you have at least 7 levels, or 10 levels, or 5 levels. Different people use different rules of thumb. And all of those levels or categories have to be fairly well represented. So a lot of times people will make a Likert scale and they'll be like from 1 to 10. They'll have 10, like strongly disagree, somewhat strongly disagree, somewhat disagree, a little bit disagree. You know, they'll make all these different categories between 1 and 10. But when you actually go collect data, only the top 3 are ever used by any person. So even though we have put 10 stop points on this Likert scale, only the top 3 get used. So Likert items are very problematic in that because of if you have sparsity or not very many people endorsing some of the levels, or you only have 3 levels. So sometimes you'll see disagree, neutral, agree. There's only 3 levels on that continuum. Can you really treat it as if it's continuous interval? A little harder to argue for that. So Likert items are notoriously hard to argue whether they should be interval or not. So that's the distinction between ordinal and interval, and it is a fuzzy boundary there sometimes. Because a lot of times Likert items, we ask people a question and they can only answer on, say, these 5 different responses, but really, what is the thing we're trying to get at? The underlying factor. Agreement is really a continuous thing. Do you agree with a certain policy? There's a continuum, but the way we measure it, we only allow for certain stop points along the continuum. Another one is age. Is age what type of scale? What would you say? Age. Say we're looking at elementary school children and we're asking their age. Is that nominal, ordinal, interval, or ratio?
Wouldn't it be ratio? Isn't there a true 0?
Age has a true 0. It does.
But?
And 1 year is 1 year. Is there a but? Can anyone think of a but?
We don't typically use the full measurement, like we group.
How do we usually collect age? If you ask someone their age, what do they usually say?
Like the year, not any months.
A whole number year. And if you're saying just a whole number year, is that really getting at the full continuum? The underlying age is a continuum. I am 42 years, 3 months, 5 days, 3 hours. You know, we can get very specific, but if we only round it off to a whole number year, that's not truly continuous. We've discretized or only collected on a measurement scale that is a certain stop point, whole numbers. So a lot of times what we'll do with kids is we'll ask not just how many years old they are. If we're looking at a little range of ages, we'll actually find their birth date and the date and subtract them to get decimal years or number of months. A lot of times we'll do how many months old a child is, because that gives us more fine-grained measurement instead of just whole number year. So age is a continuous interval ratio scale, but the way we capture it might be more categorical in nature. And so when we talk about the scale, are we talking about the true thing we're trying to measure or the way we actually gather information about that thing? And you can, time, weight, distance, all of those things are truly continuous interval ratio, but we might measure it in a more discrete way. So I talked about temperature before. Celsius and Fahrenheit are interval numeric continuous scales. Are Fahrenheit and Celsius ratio scales?
No, because there's not an absolute 0.
Absolute 0. Let's see, can we think back in our science classes? Absolute 0 in temperatures. Anyone have anything going off in their brain? Absolute 0 temperature.
So the Kelvin scale, right?
The Kelvin scale, yeah. My minor in undergrad was chemistry. taught chemistry for some years. The Kelvin scale is not used in day-to-day life mostly, but it is used in sciences because it's an interval ratio scale where there is a 0 point. And it measures, so Celsius and Fahrenheit are temperature scales that have been developed with reference points on freezing or boiling, or they've been developed with certain markers. But Kelvin scale looks at not just how a temperature compares to the boiling or freezing point of water, but in relationship to how fast the molecules are moving in any kind of matter. And the faster molecules are moving, the hotter it is, and the slower they're moving, the colder it is. So instead of really measuring hot and cold, they're measuring kinetic energy. And when the molecules, if we could slow the molecules down to the point where they were not moving at all, that's absolute 0. So in the Kelvin scale, there's actually a true 0 point. Now, so Kelvin is truly an interval ratio. Celsius and Fahrenheit are interval, but not really ratio. But here's the reason that we even talk about all this stuff, is when we do mathematical steps, add, subtract, multiply, divide, square root, all of these calculations, those calculations are not appropriate unless the numbers we're adding, subtracting, multiplying, dividing are interval ratio scales. So we shouldn't really do an average of Celsius degrees unless it's an interval ratio, which it's not. So if we have a measurement that's an interval scale, we're usually okay. It's the problems we run into are when we have ordinal scales and we start doing things like averaging. So if we have, so what's one of these ordinal scales? So maybe we have grade, first, second, third, fourth, fifth grade. If I have a group of kids, I ask them what grade they're in, and I do the average, and the average comes out to be 2.4. What does that mean? We can't have grade 2.4. Grade is either 2 or 3. There's no such thing as a grade 2.4. So this is a problem when we start doing math, add, subtract, multiply, and divide, on things that were collected in an ordinal scale. Would it make sense to do the average color? I can assign red to be a number 1, blue to be number 2, and I could come up with an average of 1.3, but would that have any meaning? No, so that's why scales of variables are very important, because knowing what type of scale a variable is measured, that alerts us to what kind of things we should or should not be doing with that variable. And we're going to learn of a lot of ANOVA-based methods, and there's a difference between categorical, discrete, nominal, ordinal, that kind of variable, versus continuous numeric interval ratio numbers. Which one works and which one doesn't? Which one is allowed to be an independent variable? Which one's allowed to be a dependent variable?
Just a quick question.
Yeah.
So you've gone over the difference between categorical and numeric, but between interval and ratio, is there any difference in how we can use those for statistics?
Usually if a variable is continuous, when we say continuous, which is a word that you're going to see a lot more in statistics, is a continuous numeric variable, it implies that it is both interval and ratio. A lot of times it's interval, but not quite ratio. We really don't have a 0 point, and that's we usually kind of overlook that in most of our mathematical calculations. But you have to be careful if you say something, you can't say double when there is no 0. So
Right.
That's the problem with ratio. So if a temperature is 10 degrees versus 20 degrees, is the 20 degrees double the temperature is 10 degrees?
No.
It's more an interpretation issue there with ratio, whether we can say double or triple, or than a selection of methodology.
Okay.
But for chapter 1, we more want to just know about the vocabulary and which words to use. The implications will come up over and over in every chapter.
Okay.
Good comment. Yeah, Kimberly?
So I'm wondering about the variable while you've been talking, like family size.
Yeah.
So that's definitely discrete, but you always hear, you know, that we have the average family size or household size of 2.8, say, which of course doesn't make sense, but I've just assumed that's just because it's a theoretical number, not necessarily because they're not supposed to get an average. So like, so is family size, because it's discrete, more ordinal, or is it because, or nominal even, I guess you could say you're in this category because you have 2 in your family, or this category because you have 3 in your family?
Yeah, this is where the lines are a little blurry. So family size, in reality, you cannot have a family size of 2.8. You cannot have 2.5 kids. But we do that math of doing the average and treating it as if it was interval ratio. Now there is a true 0 there, and 1 versus 2 is one more person, and 5 versus 6 is one person. A person is a person is a person, no matter what numbers it's between. So it's interval ratio. So we treat it as if it's numeric, even though it's discrete on a level, meaning that we don't actually have 2.5 persons. I mean, if you're pregnant, you don't say our family size is 4.1. You know, it's 4, but it will be 5 or something like that. So there is some fuzziness there. Now, it's the Likert items is like that when we have something that's discrete, but we go ahead and do the arithmetic, the averaging, and the standard deviations. We can go ahead and do those, but we need to be very careful about how we interpret the numbers, because the average family size 2.8, that's like the long run average or the overall population average. That doesn't mean that any one family actually has 2.8 people. And so knowing that it is discrete keeps us from going to the point where we say there is a family of size, that the most common family size is 2.8, because no family is 2.8. But yeah, the verbiage is more what I want you to get here, and it helps us think in terms of what we're measuring. It's not always as clear cut as you would think that it could be. Yeah. So a lot of times we make the distinction for categorical variables that they're nominal or ordinal, whether they have order or not to the categories. But usually with a numeric variable, we don't really make that distinction in day-to-day statistics between interval and ratio. We just treat it as if it's both most of the time. And even, so this is the thing with age, this note down here, even if something we're trying to measure is truly continuous in nature, we only have the ability to measure it at discrete or whole numbers or different units. Same thing happens with, like, say, in psychology, depression. A lot of times we want to measure how depressed someone is and monitor that over time. How do you capture that? This is a really big issue in social sciences. How do you put a number on something that you cannot physically measure with, like, a measuring tape or a thermometer? And so usually we ask different questions, either yes or no, or a rating scale, or Likert items, and we try to average that and try to get an estimate of that continuum, but we can't really pinpoint it as accurately or continuously as it is in true nature. Okay, so that's what I wanted to hit on, scales and variables. Does anyone want to bring up any other points about those before we move on? We can come up with a good numeric way to remember these names, that would be great. This diagram has been the best diagram I've found thus far. I'm kind of a fan of it, but how to remember it, I'm not very good. Okay, so the next one I want to hit on, and you probably talked about observation versus experimental study design in your prerequisite or co-requisite research methods course, but just wanted to hit that again. Observational means that the participants choose, or it's outside the researcher's ability to randomly assign things. So sometimes if you're thinking, you're trying to determine if it's observational or experimental study design, think what was the determining factor in which groups people end up in? Did the researcher put people in groups? And that's,
About this.
yeah.
In the textbook, it said that observational was the same as quasi-experimental, but in my prereq class, it talked about quasi-experimental is really just when you have still the researcher manipulating the study, but they're not randomly assigned to groups. It's more.
So the phrase quasi-experimental is used in different ways. I found in different niches. The quasi means not quite in my vocabulary. So it's somewhere in between these two. So sometimes quasi-experimental is meant that the researcher assigned, but not randomly. Experimental does not demand randomization. Randomization is the gold standard, but just because something is an experimental study does not mean it was assigned randomly. So here on this little arrow, it says researcher assigns the group, often randomly. Sometimes quasi-experimental phrase is thrown around if it's non-random. It's also thrown around, I found, in places where we've randomized not at the observational unit. Like here's an example. In educational research, say we want to test the current way of teaching something versus a new way of teaching something. And we want some kids to get the old method and some kids to get the new method. The researcher will decide that. But do we usually randomize or decide on individual kids? Usually we have to do it to the whole classroom, right? Or the whole teacher or the whole school. So we will make the assignment at a higher level or as a group instead as individual units, the individual kids, even though our outcome is going to be measured on individual kids. And so we call that a clustered design sometimes, or a hierarchical design, something that I do a lot of work in, and we use multi-level methods to correctly analyze that data because it's kind of a little nuance that's not trivial. But so that quasi-experimental is sometimes used for those randomized at a higher group or a greater level instead of the individual on which we're going to measure the outcome. Yeah, that's the most common place I've seen the quasi-experimental phrase used. Observational usually is that the researcher has no control over, like gender or prior family history, things that, do people choose to do exercise or not exercise versus being put in an exercise group and told that they cannot exercise or they can exercise. So is that choice made by the participant or by the researcher? And it's not like that the person really chooses to exercise. Maybe they're not exercising because they have back hurts because they had something else. It's outside of the researcher's control is the main thing. Okay, I've added a couple slides here and they're very, very bland because I just threw them in here right before class based on your discussion. So in the discussion, there was some talk about population versus parameter versus sample statistic. And this is where I like the alliteration. Alliteration, is that what it is when they start with the same letter? So the population parameter is a number that applies to the whole population that we wish to study. And the sample statistic is a number that applies to just a subset of the population. So when I say average, we could have the average for the whole population, or we could be talking about the average for just a sample. Average by itself, or standard deviation, or mean, or range, that does not tell you whether it's a parameter or a statistic. It's who it applies to that tells you whether it's a parameter or a statistic. Did anyone want to, was there some confusion or questions or anything we want to talk about here?
I think the biggest question was, how did that relate to parametric statistics versus non-parametric statistics?
Which is the next slide.
Oh, well, there you are.
Okay, so the distinction with parametric, and this is kind of a chicken and egg discussion. We don't talk about distributions in chapter 1. They come in chapter 2 and 3 and 4 and so on. But a distribution or parametric distribution is when we have a set distribution that we're assuming that something follows. And the most famous one and common one that we run across is the bell curve, the normal curve, right? And I really want to hit home, normal is not right. Being normal is not good and it is not correct. It is just something that occurs in nature a lot. And it happens a lot when we take samples. If we were to be able to gather the height of every student, male student in Utah State, I'm going to simplify a little bit, though at Utah State, all the men, we would find, if we could plot that in a histogram, we'd have roughly a bell curve, the normal distribution. Happens a lot in nature. I didn't say all students because there's probably a bell curve for men and a slightly different one for women, and if we merge them together, it's not going to be one bell curve. But if we assume that a population is following a bell curve or some other set distribution, a smooth curve to the histogram, then we are talking about a parametric distribution. The normal distribution is what we call it a two-parameter distribution. To be able to know, if you know the mean and the standard deviation and that it's normal, you could perfectly draw the plot of the histogram or the density curve that the histogram would be close to. All bell curves are exactly the same. All normal curves are exactly the same except for their mean and their standard deviation. The mean is the center of the curve. The standard deviation is how wide it is. But if you know those two numbers, you can draw the plot exactly. That's a parametric distribution. There are other distributions that we're going to go over in this class. There's a chi-squared distribution. It only has one, and the Poisson distribution, it only has one parameter. Its mean and standard deviation are the same number, and it's skewed. But it also has degrees of freedom. There are some of these other distributions that we're going to come across, but if we're talking about basing our numbers on a specific distribution, that's when our statistic becomes parametric. If we have an interval ratio scale, this is really, really handy thing to do, base our information and our tests, oh, I got a typo here, I just noticed, on a set distribution. It makes our inference, our ability to do some calculations more powerful as long as that's an accurate, that distribution is accurate to the scale we're trying to measure. Not everything is normally a normal distribution. Like I said, male and some females' heights tend to be a little bit different. Males by themselves tend to follow a normal curve, and female do too. But if you were to put them together, you'd get like this like bimodal kind of not quite a bell curve shape. And so if you treated the combined male and female population heights as a single bell curve, that would be inaccurate. Other things are like the number of tattoos each student has at Utah State. If I was to make a histogram of the number of tattoos, would it be a bell curve at Utah State, do you think? Where would the peak of that distribution be? Or the bulk of students fall? I see some pointing, yeah. They'd probably be 0, 1s, 2s, but we probably would have some skewness or some extreme cases that might have 100. In that situation, if we treated the population as being normally distributed and followed that assumption, we would get some really flawed results. And so parametric can be more powerful as long as it's an accurate depiction of the population. And things like outliers or skewness can really affect that. And we will cover that in chapter 3 ad nauseum. So here they're just kind of bringing up that terminology, and it's hard to bring in that vocabulary without some more information. The non-parametric usually means we're not going to base our stuff on a set distribution. And so with ordinal and nominal scores and scales, they usually don't follow like the bell curve, so it would be not right to do that. It makes it more flexible, but the key is it's not following a set distribution. Good? Okay, so that will come back as we move forward. Most of the methods we're going to learn in this class are parametric tests. Almost every test quantitative method has a parametric way of doing it and a non-parametric way. There's the t-test, and which uses the mean, and a Mann-Whitney U that uses the median. So there's different ways to do things depending on whether you're going to assume a set distribution or not.
Oh, sorry.
Yeah.
Let me ask a quick question while we're right here. So
Yeah.
you did say chi-square was non-parametric, right? Is that what I heard?
Chi-square is parametric. It
It is
has
parametric because
one
it's a set
parameter.
distribution.
The set distribution.
Okay.
So in the
All right.
back of our textbook, there's the Z table for the normal distribution and the T table, and there's all these other tables, chi-squared, F. Each of those tables is for a set distribution. So any of those are parametric.
So chi-square, even though it's on nominal data, would still fit under
Well,
parametric because
we
of...
can use it, the chi-squared, we use it on the test statistic, which is the sum of the squared deviance of the cells.
So that's why.
That's why we use a
Okay.
chi-squared. Yeah.
That's cool. All right.
Don't worry, Kimberly's a little ahead on that question.
No, I'm sorry.
Yeah. No,
I was like,
we're
holy
trying-
crap.
Yeah, we're all trying to
Exciting.
digest this at different points.
Okay.
So exciting to read Kimberly's responses though and things because I don't understand them. Like I'm sure they're helpful as well, but I love where you are.
I'm sorry.
You guys
Just because
don't
I
know-
know math does not mean I know statistics, though. Please understand that. They are apples and oranges sometimes.
Kimberly, you've been teaching statistics for how many years now?
20.
Yeah.
But like undergraduate, not graduate level for sure.
Still.
Well, we need the early elementary K2 version.
Yeah, and it's okay. I loved the comment. I can't remember who said it, but who was it that had used this textbook for another class? Yeah, and that you said that this time you didn't know that there was a place in your brain for it to land. And that's that idea of scaffolding. So everyone's coming into this class with a different scaffolding in your brain, a different level of experience. And the difficulty or easiness that anyone finds with any topic is not based on the difficulty of the topic. It's more on your experience surrounding the topic. And so even though parametric, non-parametric, that distinction is clear in my mind, that doesn't mean that it's going to be clear in everyone's mind. And it has nothing to do with I'm smart and you are not. It has to do with the experience you've had regarding those words and using those words in different ways. And so please, nobody ever feel like I got to ask a dumb question. I don't want to, because we're all digesting and trying to put this in place into what we already have in our brains. I used to teach Math 1050 for the math department, and I taught it a lot in the night classes. And it was always a mixed class in that we'd have some students that were like straight out of high school and other students that were coming back to their education later in life. And those older students were always like so apologetic. They're like, I know I've forgotten and I should know this, but no, they would always feel bad that they had forgotten so much and they were asking basic questions in their eyes. But they tend to absorb at such a deeper level that they got so much more out of the class than those straight out of high school young whippersnappers. So don't feel bad about where you're at.
That's where when I took it, and I loved Math 1050. It was a great class.
I'm a math nerd, I like it. Okay, rounding numbers. Okay, we don't want to take too much on this. So there's 3 bullet points under rounding in Cohen Presents. And these rules, the first 2 bullet points are the same ones you learned in elementary school, right? When you want to round it off, wherever you're rounding it to, you look at the next number. If it's bigger than 5, you round up. If it's littler than 5, you round down. The new catch is this 3rd bullet point. If after where you want to round it up, if after that spot is a 5 and only a 5 and nothing else. In elementary school, we were told to round it up. The problem we run into is that you're rounding up for 5, 6, 7, 8, and 9, and you're only keeping it the same with 0, 1, 2, 3, 4. And so you're rounding up more than half of the time. And so to kind of balance that out, if you have exactly a 5 and nothing else after the spot you're rounding, you only round up if where you're rounding is odd. And so this is different than you've learned. And I'm not a stickler on this rule, but the book presents it, and a lot of software tends to follow this. And I more want to make you aware of this than to like beat you over the head with this, okay? So this, sometimes you'll see something rounded off and you're like, that's not how I would have rounded it. Just know that there are these other rules in place that other software and other people use traditionally, but I'm not going to get really nitpicky about it. So some examples.
Sarah?
Yeah.
So if you had a number and the last, the place value you want to round it to it, the number after that, there's a 5 and nothing else, that's when you use this rule.
Yeah, that's when you use this rule.
Okay.
So I'm going to come into the student view on Canvas, and I'm going to go into the first assignment that has, and so we're going to look at some examples, the homework examples. So assignments, because I don't have any new examples, figure we might as well do the ones you're already doing. So homework 1. So if you haven't gone into the Canvas assignment, this is what it looks like when you go in. Homework 1 is ready to go. So let's see. So there's all of these things. Where's the rounding one? Ah, here's the rounding one. I'm going to make this a little bigger so it shows up. Okay, so we're supposed to round so that we have 2 decimal places, 2 numbers after the decimal. So this first A is 144.0135. So if we're going to round to 2 decimal places, we keep the 2 numbers after the decimal, and then we look what comes next. So after we would cut it off at the 1, it's a 3. So we would round up or leave it the same?
Leave.
Leave it the same. So this one, 144.01. Okay, so this next one is one of those where we want to cut it off at the 0.24. After where we're going to cut it off at the 4, there's just a 5. This is that third bullet point rule. It's just a 5. So in that case, we look at where we are cutting it off. It is a 4. That is even. You look at where you're cutting it off, if it's even or odd. So here, do we round it up or leave it the same? We leave it the same. Again, I don't want to beat you up over this and like focus on it unduly, but this is the rule that is followed by a lot of people, and you might like be like, wait a second, if you hadn't been told about it. So in the homework, you can check your answer. If it's yellow, that means that item is right, but all of them are not right. So let's see, let's do another one. That's a, okay, what about this one, E? We're going to cut it off at the 4. We look after the 4 comes a 5, but it's not just 5. So we go ahead and round it up. Oh, it won't let you type in because you have to push the try again button. I'm going to put, oh, what about this last one? How will we round this one up? 7.997. 7 means we round up the 9. How do we round up a 9? You make it a 0 and round up the next number. Well, it's a 9. So we make that a 0, and we have to keep passing the rounding up. So what's the answer for this one? 6.00. Because we've got to round up, it like passes over, carry it over. Let's see. What about D? 13.3. Do we leave the 4 or round it up?
Leave it.
Leave it. And so after you put in all your answers, I would not check your answer until you've entered them all. Then when you check your answer, it will give you green check marks if they're all right. All part A, B, C, D. And it shows you over how many allowed attempts, and it tells you how many points you've gotten on your last attempt, just in case you wanted to know.
I have a question. I mean,
Yeah.
when I looked at it, and so like this first homework, I answered the set 1A.
Mm-hmm.
Can I check my answer 3 times on that, or do I have to answer everything in the entire quiz?
It on your check your answer. So here, this check your answer button works for all A through G.
Oh, gotcha.
Let me go over to item C, or item 3. They call them item 1, 2, 3, 4 in this program. But so on
Gotcha.
this one, it's got, so this is chapter 1, section B, problem number 1, A through H. But notice the check your answer is down here. This check your answer button applies A through H all together. So I would answer all of A through H before I push this check your answer button.
So for every question, total question, I have 3 tries.
Yeah, so you can check A through H, that group, 3 times. That's why I would do all of them before you check your answer, because you only get to press this button 3 times, and then you can't push it anymore. And if you ever run into this where you run out of attempts and you know what it is, email me and I can override the scoring. So I almost put all of these on one, and I thought that's mean. So I broke it up. So this one's A through H. You can check those answers. And then down here, here's another A through H, and you can check those answers. So there's like 2 sets. These are good questions.
I'm wondering also about the downloads at the top.
Okay, these downloads at the top have to do with R. So let's hold on until we're ready to do R, and then I'll show you what you do with those.
Perfect, thank you.
So far, I'm just assuming you've downloaded R and you haven't even looked at it outside of that. These downloads are for using R. This first one is the data set. The second one is actually the code that processes the data. Okay, I think there's, yep, the rounding rule. Okay, there's any other questions on the rounding? That's a funky third rule. Okay, the last thing in this chapter, last thing other than R, right? Yeah, other than R, the last thing in this chapter is the summation notation. So that's that big giant sigma. Underneath it or out to the side underneath it, kind of, sometimes it's right underneath it, sometimes it's kind of kicked out to the side, depends on the formatting of the text, is the number that you start with, and then the number on top is where you end with. So down underneath here it says n equals 2, so we're going to start with 2, and we're going to go up to 5, and you go in whole numbers, so it would be 2, 3, 4, 5 for this example. Sometimes this is called the index, and so a lot of times it will have a little I there. If those red numbers, this n equals 2 and this 5 up here, if those are like not anywhere, like they're invisible, that means for 1 through the maximum. And capital N is how many of those indices you have. So on this one, we're going 2, 3, 4, 5. So we're doing 4 repetitions. We're going to add up 4 things. When n is equal to 2, when n is equal to 3, when n is equal to 4, up to n is equal to 5. And then here in green, what's out to the side after the sigma, that's what we're going to be adding up. So sigma is shorthand for add up. So this is saying add up n, I'm going to say add up a number where the number goes from 2 to 5. So the mathematical reading of this, add up the numbers 2 through 5. So we go 2, 3, 4, 5, add them up, and the total is 14. The reason the book brings this up now is because a lot of the formulas that we're going to be using do a lot of repeated addition, and so it's the shortcut notation that's going to show up in a lot of our formulas throughout this whole book, the whole semester.
So can I just ask a clarifying question?
Yeah.
So just to clarify, that number on top of the sum sign is go to this value. It's not like there are 5 values.
No, it's the one. It's the last number you will use.
Last number you will use. Thank you.
Yeah. So the bottom is the first number you will use, and the top is the last number you will use. So you do all the numbers in between, including the bottom and the top.
Okay.
So 2, 3, 4, 5. Yeah, if you've not done these a lot, it's like foreign language completely. Okay, so a lot of times here, the number, the stepping number, 2, 3, 4, 5, they're using n, and n is in the formula. A lot of times we use a little I for index, that's the math lingo, is actually a subscript. And so it's just saying which of them. So a lot of times I present with my Surface Pro, and I can write on the PowerPoint with my mouse or my pen. Let me see, let me open up Word. Now, so X sub I, like a little scratch paper here, because I don't have a board to write on. Whiteboard. Oh, small. So this xi, that means x index I. So x might be a list of numbers, and x sub I means each of the numbers in the list of x numbers. So a lot of times we'll have something where x sub 1, and I'm going to write this underscore to be a subscript. I could do, in Word, you have to then highlight it and go up here and tell it that it's a subscript. So x sub 1 means the first number in the list of x numbers. So if x is a list of numbers, 2, 4, 6, 8, 10 are the ones on the homework, I think, right? So the even numbers, 2, 4, 6, 8, 10. X sub 1 is the first number in that list of x numbers. So the first number in x is 2. So then the second number in the x list is, show fingers, the second x sub 2 is then 4. So the little subscript number tells you the place in the list. So x is a list of numbers, and the little subscript, which I is the generic index number, tells you which slot or place in that list of x. So if x is not a single number, it's actually a list of numbers, the subscript tells you which one, the first, the second, the third, the fourth, the fifth slot. So the way we would read this first one here would be adding up, because sigma is adding up the combined sum of x and y in a list. So if x is a list of numbers and y is a list of numbers, we're going to take the first two numbers, add them together. The second two numbers, add them together. Third two numbers, add them together, and then we're going to total it all. And with addition, order doesn't matter. If you add them up into the pairs first or add them up within the list first, you're still going to add them all up. And that's what the summation rule is. I'm never going to quiz you on these rules. They do some great things. As a mathematician, I love them. But more than anything, I just want you to be able to work with the numbers in a summation. So that's why here on the homework, we have some examples. So here are our x numbers, 1 through 5, and our y numbers, 1 through 5. So part A says, if we look at the sigma, I goes from 2 to 5. So we're going to start with the second slot. So we're going to go slot 2, 3, 4, 5. So how many of them are we going to add up? 2 to 5, 2, 3, 4, 5. So we're going to add up 4 numbers. Which 4 numbers are we going to be adding up? Slot 2 through 5 of the x numbers. So that's adding up 4, 6, 8, and 10. So for this first one, we're adding up the x numbers, slot second, third, fourth, and fifth numbers in the list of x.
So do we just know which ones are adding up by what the problem is asking for? Like, okay, we're going
so
to.
This has to tell you, so on part A, notice the sigma, it has I equals 2 to 5. So you know you're not going to do the first number. You're going to start with the second number.
Right.
You're going to do x sub 2, and then you're going to keep going until you get to x sub 5. And you're going to take those numbers, and the sigma means add them up. Sigma will always be adding them up.
Okay.
So does anyone have a total for that one? 28. Saw the lip. I can read lips a little bit. No, I can't. So part B. Now we're not adding the x numbers, we're adding the y numbers, but we're going to start with the first one and go till we get to the fourth one. So we're going to add 3, 5, 7, 9, stop. 34 or 43?
24.
35. Anyone agree? 3 plus 5 is 8, plus 7 is 15. Oh, I got 24. Yes, those, but see, you don't want to use your check your answer early because I've used my check my answer, but I only had 2 of them in, so I don't get any feedback on the rest of them. So don't do that. Okay. All right, so those first two. Now on C, the sigma doesn't have any number underneath it and any number on top of it. So if those I equals starting number to ending number are missing, that means do all of them. So on C, it says 5xi. What does it mean when we have a number sitting right next to a letter and they're just squished together with nothing between them? Yeah, it means multiply. So this means 5 times, so we're going to do 5 times each x number, and we're going to add them all up. So you're going to take your x numbers times each one of them by 5 and add all of them up. All right. Okay. All right. Whew, do we need a 5-minute break? Let's take at least a 5-minute break, and when we come back, we're gonna open up our studio and we're gonna use it for the first time ever.
Before we move into R, can we talk? I put a little asterisk by that next one in the summation rules. I don't understand what the constant thing is.
The constant is a number, like here in part D, question D, the constant C number is 3. It's a number that doesn't change for each of them. So we're doing 3 times every number.
Okay.
3 is the constant number. Constant is the opposite of a variable.
So it'll just be somewhere in the problem. If there's any problem that applies to each of those, or any number that applies to each of those, we consider it a constant.
Yep. So in the rule here, it says, so this is number 3 rule. So it says if we have a constant, the same number times all of our variable numbers, variables change. It's the same thing as adding them up plain, just adding them up plain, and then timesing the total by the number instead of, you can do either way. So on this problem, D, you can times each of the y numbers by 3 and add them up afterwards, or you could add them up first and times the total by 3. You'll get the same thing.
Thanks. I just didn't understand that vocabulary. I couldn't figure out where I was supposed to find a constant. What does this mean? So that's perfect.
Yep. For these problems, you don't have to follow the rules, but you can refer to them if you want to.
And will you go back to just your summation rules?
Yes.
PowerPoint page. Thank you.
Yeah. Let's stick theirs up.